Okay, so we have just a second here. Oh, okay. 1 second here. We are having a problem here. I'm going to stop. Uh, um, Kiara, if you're on, I've got Fathom recording, but it's holding me up on a meeting passcode. I'm just going to go ahead and cancel that so that we don't delay this. Uh, I want to get started right away here. All right. Great. Welcome, everybody. We are going to be talking about petabyte scale data in real time using ClickHouse, S3 object storage, and data lakes. This is a subject near and dear to our hearts. With me today is Alexander Zaitsev, and we'll be presenting some of the latest experience that we have working with customers on this topic. Before I get into this talk, though, I want to just bring up a couple of housekeeping things. First of all, this talk is being recorded on Zoom, so you will get a link to the talk recording as well as the slides within 12 to 24 hours of the completion of the webinar. Second thing, we do have a chat box, which is available, and I see somebody has already typed something in. We also have a question and answer box. So if you have questions during the presentation, please go ahead and put them in either of those locations, and we'll take them either as during the talk if they're directly relevant to what we're talking about, or we will have some time at the end. I think that concludes the main messages. Let's go ahead and dig in. So once again, my name is Robert Hodges. I am a database geek. I've been working on databases actually for about 40 years, uh, and then Kubernetes since 2018. I'm CEO of Altinity. I have with me today Alexander Zaitsev. He is the Altinity CTO as well as a founder of Altinity. And as you can see here, he is an expert in high-scale analytics systems, design and implementation. He actually did one of the first major implementations in the United States of ClickHouse. And Altinity is a company. We're an enterprise provider for ClickHouse. We focus on support and services for building real-time analytic applications. We have a cloud, Altinity.cloud, which was the first cloud for ClickHouse in the Amazon market, as well as GCP and Azure. We also do Altinity stables. We wrote the Altinity Kubernetes operator and a number of other useful bits of software that you may have heard of or use, including ClickHouse Backup. So that's us. Let's dive into the topic at hand. So in this first section, I'm just going to briefly introduce the real-time big data and some of the problems that are now arising in systems that we see. So let's have a look at a specific problem. Application monitoring is one of the most popular use cases for ClickHouse these days. So you may be building a system where you're collecting metrics from applications that you're running in your own data centers or VPCs. You're ingesting them into a database like ClickHouse, and you're enabling query on them, including visualization, alerting, and other types of consumption. If we look at the requirements for a typical application, they're shown below. So things like, hey, we have 200 bytes per record coming in, and we would like to, we'd like to read them at the rate of 300 million records per second. That is not an uncommon rate of rate of ingest, retain them for 365 days. We have some query, sort of response time queries, response time on queries. And we also have growth because these large systems start out at a certain size, but they never remain there. The most common way that systems scale is by adding more storage. So you put this together and you run a little math, and just the storage alone creates some really interesting issues as you're building this system, because you get a compounding effect from adding all this data. We're going to keep it for 12 months, but if we go ahead and take those requirements and chart them out, just for the data alone, we're close to 3 petabytes of data being stored and queried at the end of a year of operation. And this is making some assumptions like pretty good compression, in this case 90%. This is big data. There are, of course, similar things could be said about query. We won't go into those because we're particularly focused on storage in this talk. So let's just introduce ClickHouse. I think most of the people on this call are familiar with ClickHouse. And by the way, for anybody who's joined late, this call will be recorded and you will get a link afterwards, so no need to scribble notes. So introducing ClickHouse. So ClickHouse is a real-time analytic database. It is, and by that we mean that it is designed to give very rapid responses close to real time on very large data sets, often with data arriving very quickly. So it's kind of like MySQL in the sense that it understands SQL, it runs practically everywhere, it's open source. It's kind of like a traditional data warehouse, like Vertica back in the day, in the sense that it was originally designed with a shared nothing architecture, it uses columnar storage, parallelizes practically everything. It's wonderful about soaking up resources, for example, on CPUs, and it scales to many petabytes. However, as you'll see in this talk, there's a little bit of thought required to do that. How does it work inside? So if you're just setting up ClickHouse or if you've used it on smaller systems, you see an architecture that looks like this picture. So we have the ClickHouse processes. Um, they run as individual servers. We'll typically run them on different VMs or different hosts. And they can manipulate two different kinds of storage. Traditionally, smaller ClickHouse systems have used block storage, either locally attached, for example, NVMe SSD. In the cloud, increasingly, in fact, for us, predominantly elastic block storage or similar cloud block storage available from your provider. And then over the last few years, ClickHouse has also been extended to be able to use and access data that is stored on object storage, beginning with S3 compatible object storage, but in modern ClickHouse versions, it can also go directly through, for example, GCS APIs. The coordination of this, it replicates data between copies of data between servers. That's handled, that consensus that's necessary to describe what needs to be replicated is handled by Zookeeper. We won't speak of Zookeeper very much from here on out, but this is the basic architecture of the system. So if you just go ahead and build that monitoring system, with this architecture, you're going to run into some problems. And if you're just using, for example, block storage, or God forbid, you should try and put all the data on NVMe SSD, the problem you're going to run into is the data set size is basically growing without bound. Moreover, the need for compute is going to grow similarly, because as your data set gets larger, there's a good chance you're doing more heavier queries on it. So the question is, how can we deal with that in ClickHouse? And that's what we're going to explore in this talk. So let's start with kind of a way of thinking about the design for implementing analytics on big data with real-time response. How do we do it? So there's actually a fairly good process for doing this. The first time that I saw it personally was in a presentation from Cloudflare. They've been doing this for a long time. Very early on, they and other people figured out a way of designing these systems where the eventual system is much larger than you can conveniently set up on a laptop or even on a few hosts. So you have to have a way to attack this problem. The first thing is just figure out what your requirements are. In that example I gave in the previous slides, we know what our approximate ingest rate is. We know how long we want to hold the data. We can make some assumptions about compression, for example, and most importantly, we can make assumptions about what the data growth looks like. This is very important because data doesn't stand still. You add some data, system becomes successful, and it's going to grow. So having those numbers in mind then enables you to take the first step. And what you want to do is test the core of your system, ideally a single ClickHouse server, to just figure out capacity or figure out the maximum capacity that you can get out of a single server. So if necessary, if you have requirements that have to do with end-to-end latency or other types of things that involve upstream or downstream data, you'll also add ingest and perhaps query facilities to this, because you want to simulate the end-to-end operation. But the key thing here is to make this as small as possible, just one thing that you can basically hammer and figure out what the capacity is and get that as optimized as possible. And then finally, you take that, once you've got that, you can just take that and multiply it. And that's what a lot of this talk is about, is how to scale things out. Once you've got one node working, you can now build a system that could run to 100 nodes. But because you've got the basic, the first node working, and sort of understand how it works end to end, you're now in a good position to scale this out linearly. So here's the capacity testing loop that we recommend. So what you're going to do is you're going to go ahead and deploy an initial schema and perhaps an application. You're going to put load on the system. So you're going to ingest data, you're going to query data, ideally at once. Ideally real data, so not test data, but data that is truly representative of what you're going to be processing in this system. This is very important to get right. And also, and that includes ingest rates, includes amount of data, so on and so forth. Put that load on, run the test, analyze the results, go in and say, okay, where were the bottlenecks? Where did I run out of capacity? And fix those. As it says here, adjust the design, and then do it again. And you just keep looping through this as fast as you can until you basically have done all the optimizations you obviously can. And at that point, you have kind of a capacity, an established capacity for a single ClickHouse host. So what are those optimizations? Well, here's some of our favorites. The first one that we always look at is just reducing I/O. Fix your schema. So get to that. If you assume 90% compression, I put that on early on. Use codecs, change your sort orders, play around with compression to get that to get those numbers as low as possible. Other things you can do are just reducing queries. For example, not having a lot of joins, but as much as possible, reducing queries to a single scan. This means that your response tends to be closer to linear with the amount of resources you apply. That's a big reason for doing this. The queries themselves often need optimization, and then all the way down to doing things like adding CPUs and RAM. Many queries simply won't run if they don't have enough memory. So establishing those sort of bottom limits, as well as the, how much you really need to scale that before the system works reliably. Those are all important things to work out while you've got this single server. Once you've hit that point, you can now think, when you've got the core of the system working, you can now think about going big. And at that point, you can begin to look at three major things, which we'll talk about for the rest of this presentation. First is to ensure that you have flexible scaling that includes both vertical and horizontal scaling of your compute. So this is very important, because as more load gets put on the system, as you add more data, you're going to need to add more compute to access it. Second thing, you can take the MergeTree tables, that's the workhorse table in these systems, and you can extend it by allowing it to write data onto S3. So that's going to give you access to cheap and effectively unlimited storage. The final thing is to look at options for reading data out of data lakes. ClickHouse is a great database. It organizes data very efficiently, but the data doesn't have to live inside ClickHouse for you to query it. It can live in Parquet out on S3. Moreover, there's some advantages beyond scaling ClickHouse. This is data that other people can access as well. So what we're now going to do is dive into each of these topics and show how to set them up. And for the next topic, I'm going to invite Alexander to come in and talk about implementing flexible compute.
Thank you, Robert. So since we want to go big, right, we need to make sure that we can provide enough resources to our ClickHouse installation to handle the load, and the data grows, so we cannot know in advance what kind of resources are required. We may start with enough resources, but in a few months, the amount of data is so big that our server or cluster is not sufficient, and we need to scale. And the scaling capability should be very accessible and easy to do, because moving ClickHouse to a different hardware or somewhere else is a difficult exercise. So it needs to be something simple. One thing that immediately comes in mind is public cloud. In public cloud, it is very convenient to scale compute. You just need to request a new machine. And if you use network attached block storage, you don't need to migrate your data at all. You can reattach the new virtual machine, new EC2 instance, if we are talking about AWS, to the same storage, and it will continue to work. The full scaling up process may take just a few minutes. First, you request a VM. Once you have a VM, you just install ClickHouse and reattach the volume, and that's it. It may take even 2 minutes in the best case scenario. And when you scale in VM, you can add more CPU, you can add more RAM, and alternatively, you can also scale your storage. Why not? It's kind of obvious, especially if you have network attached storage, you can increase the size. And if a single volume is not enough, you may attach multiple volumes to ClickHouse. But you can also scale throughput and IOPS in many cases, which also increase your performance and ability to handle more data. Second slide. The vertical scaling is often not efficient and not sufficient. As your data grow, single box never can be enough. And ClickHouse provides two ways of scaling your cluster or your system, and of two dimensions. One dimension is adding more replicas. This is more traditional for databases. You add more replicas in order to handle more QPS, more queries per second, more concurrency. It doesn't help you much with the data size, but if your queries require quite a lot of resources, then adding more replicas may help to improve the overall system performance. Another direction, which is much more interesting, is adding more shards that allow you to scale your system almost unlimitedly. So every shard in ClickHouse will store its portion of the data. So if your full data set is 1 petabyte, you may deploy, 100 shards and store 10 gigabytes per shard. And ClickHouse can efficiently query such big clusters. When you add shards, you not only add more space to store your data, but you also increase your capacity in terms of CPU power, in terms of throughput, because even with a very fast storage, say you read 1 gigabyte per second for storage, and this is your maximum. When you have 100 shards, your overall read speed is 100 times more. It's 100 gigabytes per second. This is already very fast. So for the big data, if we're talking about hundreds of gigabytes or even tens of gigabytes, hundreds of gigabytes and petabytes, sharding is the must go. And it should be easy to do in ClickHouse, and it should be easy to manage. Let's see how to do it on the next slide. So what we have discovered in the last years that Kubernetes is a great technology in order to manage cloud resources. Not to manage, it's not for orchestration like it has been originally developed, but it's for management of cloud resources. Inside Kubernetes, there are abstractions for different things, like there's a pod. This is abstraction for compute. And what Kubernetes in public cloud can do is to map this pod abstraction to an actual VM. If we create a pod, then Kubernetes communicates to the cloud in order to provision a virtual machine and then deploy this pod to this virtual machine. This is very convenient. Same for volumes. There is a persistent volume abstraction in Kubernetes. You can create this abstraction, and that will be instruction to the cloud provider in order to provision volume and mount it to the pod. If you have pod with volume mounts. So Kubernetes in this scheme is a management layer that provides a convenient API to manage cloud resources and makes it very easy to scale cloud resources, compute and storage. Next slide, please. But if we're talking about ClickHouse, then it's not very easy to deploy it in Kubernetes. Because ClickHouse cluster, it consists of multiple shards, multiple replicas, so you need to create a lot of pods. Then you need to create a lot of persistent volumes and mount them to the pods. Then you have configuration. You need a way to deploy configuration. This is probably config maps, and so on and so forth. A lot of different Kubernetes objects or objects abstractions that are required in order to create a ClickHouse cluster. In order to make it easier, Kubernetes provides the very convenient extension, which is called custom resource definition. And for those custom resource definitions, developers may develop operators that understand those custom resource definition and kind of implement special logic in order to process them. In the case of ClickHouse, this is what we do with Altinity operator for ClickHouse. I will show you in a second, but the idea is that you have the definition of your cluster, which is written in JSON or in YAML, and operator understands this definition, and based on this definition, deploys a bunch of different Kubernetes resources that represent your ClickHouse cluster. And if you change the definition, then operator applies the change. So you don't need to care about all the wiring. It is all done by operator. So say on the next slide, we want to scale the compute. So this is an example. This is a very small part of ClickHouse installation manifest that defines that we deploy ClickHouse with M6I large instance type. And on the next slide, we can change this instance type to a different one and apply this change to the Kubernetes, and operator will see it and reschedule our ClickHouse on a bigger node. As I said earlier, this process is pretty fast. It might take 2 minutes for a single shard server. And if we have, I don't know, 100 of shards, it will of course take longer, but this is exactly the same change. You don't need to change to do 100 changes. You change it in one place. I want to change my instance type, and that's it. Next slide, please. Similarly, we can do horizontal scaling. This is an example of ClickHouse installation that defines a cluster with 1 shard and 2 replicas. And what if we want to change it to something bigger? You just change the number. Here we have 2 shards, 3 replicas. Operator will see it and will try provisioning new scheduling new pods that will in turn trigger provisioning new EC2 instances and new volumes and so on and so forth. This process again takes not too much time, probably 10 minutes, and you have a bigger cluster. Of course, your new shards don't have any data, but replicas will do. It will replicate automatically. More than that, Kubernetes allows us to mix and match different compute and storage patterns. We may have the local and storage and compute. We may have object storage attached to the compute. We may have even object storage which is located in totally different cloud account, which allows you to make a full separation of resources. Say you have your data somewhere already, and you want to spin a cluster to process it. You can do it in a different account. That's very convenient. It's not only a property of Kubernetes; it's property of Kubernetes in public cloud, and we hardly advocate you to use it. It's much easier than do it manually or develop your own infrastructure to manage compute and storage for ClickHouse. Next slide. Okay, I'm done here, and Robert will take the next one.
I'll take the next one. And we do have some questions coming up. So Alexander may answer some of them in the background, but we'll also reserve time at the end and definitely hang around to answer every question that you have. What I'm now going to do is talk about the second part after compute, which is actually scaling the size of MergeTree tables using S3 storage. So let's dig in. First thing we want to do is let's just remind ourselves, how is it that ClickHouse actually deals with regular block storage, attached storage? So you look at ClickHouse, you define a table, you're going to use the MergeTree table engine that, as I mentioned, it's the workhorse engine for big data. That data is actually stored out on a file system, maybe one volume, maybe multiple volumes. It consists of metadata, which is the table definition and the names of files, and it also contains table data, the actual bytes in, for example, a table part. There will be a file, of course, two files normally for each column. You look inside those files, it's a binary format containing bytes of compressed data. So those then are read from the host. A really key feature of this is the operating system page cache, which allows us to, so when we read from storage, the Linux operating system will automatically populate pages into that. So that if we reread them a short time later, chances are we'll get them out of RAM as opposed to having to go to storage. Key things about this organization: it's columnar. The columns have encodings starting with their data types, but also functions like delta, which allow us to reduce the data size before it's turned over to the next feature, which is compression. And then we have things like ordering and what's called a sparse index and secondary indexes. All of these things are MergeTree things that are MergeTree features that allow us to query data very, very quickly. So that is the standard and the traditional way that storage is managed. So what we now have since basically, I think it's about 3 years since this really began to emerge, is that we can now not only store the data on block storage, but we can store it on object storage. Object storage has some big attractions. The first and the most obvious is it has unlimited capacity. Instead of having to worry about volumes which have fixed size, and it's true you can extend them, although that used to be a lot harder than it is now. There is a point where it just becomes difficult to manage them. S3 object storage just doesn't have that limitation. It's out on the net. You can just add stuff. You don't have to worry about managing capacity. It is a great deal cheaper than block storage, so on the order of 4 to 5 times for the storage cost. Note, however, that when you use object storage, you also have to consider API calls. Those are cloud providers also bill for those, particularly Amazon. And so if you make a lot of calls to files, to bring them down again and again and again, of course, it will drive the cost up. It is shareable across many servers can use it, and it's also now the predominant format for organizing data lakes. So, for example, storing files that are out on in CVS or CSV, or more commonly things like Parquet. S3 compatible storage also includes many things other than Amazon. So for quite some time, things like Google Cloud Storage, MinIO, Ceph, these all offer S3 compatible interfaces. Moreover, ClickHouse itself has learned to use the native APIs for things like GCS, so we can also access it that way. We won't talk about that kind of compatibility. We'll just talk about S3. It's kind of a stand-in for any of these cloud object storage implementations. So how do we use it? Well, we'll talk about how it's organized, but let's just talk first of all, like an upfront best practice. Contrary to what I just said, or what you might have thought when I said that S3 storage is shareable across many servers, we don't actually recommend doing that. We recommend that for each ClickHouse server, you just give it its own place to write and to read its S3 files. So you'll have separate copies. This has some disadvantages because you don't get the full benefit of S3, where you just have one copy of the data that's shared by everybody. But on the other hand, it's a much easier at the current the way ClickHouse is at the current state of the implementation, it's vastly easier to manage and has fewer problems. There is an alternative implementation called zero copy replication, and what this does is it stores the. To make a long story short, it has a way of storing the data in a shared S3 bucket, and then all of the servers can look at it. But this implementation requires very careful coordination. It has bugs, and is still under active development. The people who use this successfully tend to be experts and are well aware of what they're getting into. They understand how the code works, they understand their use cases, and can map them together. We don't recommend that for the general case. Just go with separate copies. Let's look at how to organize it. So the way that S3 storage is organized for MergeTree is using something called storage configurations. And this is a really flexible feature of ClickHouse. And let's start from the bottom. Basically, what you can do in storage configuration, it's an XML file. You can define what are called disks, which are basically locations for storing data. You can imagine them. In fact, they often turn out to be different mount points um, on your host. So you can describe the disk, and there's several different types that we'll talk about. There's a default disk, which is just where ClickHouse stores data if you don't tell it anything different. There's a type of disk called S3 disk, and that is a disk which knows how to read and write data stored in S3. And there's a type that is related to that called actually a file system cache. And what that does is you basically tell ClickHouse to read and write through the cache, and what it will do is it'll go look for things in the cache first, and then if it doesn't find it, it will of course go to whatever the underlying storage is. In this case, S3. So we have these different disk types. We can organize them into what are called volumes. So volumes tell ClickHouse that these are the locations for the data, and you can actually have multiple disks underneath. The cache sort of wrapping an S3 disk is an example of that, but you can also have multiple mount points. They have an order. So by default, data will go to the first of these that you list. And then finally, there's a policy which binds these together, and you now can use that policy to when you define a table to say how you'd like the data for it stored. We'll go into all of these details, and it'll seem much less complicated than it does here. So let's just go one by one. So setting up disks within this is an example of a storage configuration file. It uses this storage configuration tag. We're going to start with disks. And what you want to do when you're setting up S3 is the key thing is to define endpoints so that every server writes to a different location. A cool trick that you can use in ClickHouse is you can use macros to do this. These two macros, installation and replica, are defined automatically by the Altinity Kubernetes operator, and they will get filled in with the actual locations. And what this does is it means in a cluster, if you have, say, 100 replicas, and maybe even multiple installations that are multiple ClickHouse clusters, these macros will keep all of them separate so they write to different parts of the S3 bucket. So that's a key recommendation, to get that right and not to mix data inside the S3 bucket from different, different servers. Next, use a cache. So this has a number of benefits, and it's very easy to set up. So if we have that S3 disk defined, what we now define as a cache, which is another type of disk. We tell it which underlying storage it's attached to, tell it where to stick the data, tell how big it should be, give some other, there's a number of other options. These are typical examples. And so by setting this up, we can now refer to this later in a storage policy. And this will reduce we'll talk about some of the benefits, but the key thing is it reduces your API calls. And of course, it's faster and not just because the cache may be stored, for example, on locally attached NVMe SSD. The other thing is that because it's on the local file system, it can take advantage of the OS page cache. So without you doing anything special, you get a lot of your memory, a lot of your data just already available to you as pages in RAM. Final best practice around storage definition is to use tiered storage. And what we do here is that we basically set the storage up so that when data arrives, it goes on to a volume here called default, which is going to, in this case, be block storage. And then at some later time, it's going to be moved to S3, which is here shown as the S3 cache, because that's the thing that we're reading and writing through. So there's this thing called move factor, and that's just a setting that says, hey, when this default disk hits 90%, start moving stuff off so we don't run out of storage. There's actually better ways to move things around. I'll show you those in a minute. But this tiered storage is then a very flexible and way that we can organize this data. And we'll talk about why that is so in just a minute. But first, we want to use it. So the final part is you got storage set up. Now you got to use it in a table. So as you know from using ClickHouse, replication, many other things are done on a table by table basis. Storage is no different. The way that we choose our storage is that we want to use is we have this storage policy setting. And so we set up this table and we say, hey, we want to use tiered storage. And we have this really important clause here called a TTL move clause. And what this says is that for this data, when it arrives, as soon as the date is, whatever the date is in the row plus 7 days, let's go ahead and move it off to the to S3. And so now you have an organization of storage where it's pretty easy to reason about it, unless you have an excessive amount of data and have to clear the default disk somehow. Data arrives, goes on to default, sits there for a while. It's easy to access. Queries are fast. It can merge, and then it moves to S3 in due time. So this is very easy to set up and manage. And just a quick example of performance. This shows particularly the difference in using a cache. These are some sample queries. Check that on an older version of ClickHouse, but the behavior is no different in modern versions. So if you're writing directly to S3 disk, these queries will always have about this speed because they don't get cached. If you're reading and writing through the cache, you'll get about the same performance when the cache is empty, but as soon as the cache begins to fill, these queries become very fast. So, and then tiered storage, I don't show it here, but tiered storage has about the same performance as S3 cache, provided your data, you have good data locality and are not, sort of blowing the cache out constantly. A really important question, sometimes people want to just use S3 storage, but one of the reasons that we recommend tiered storage very strongly is because of merges. So if you put the data out straight out into S3, as you probably know, ClickHouse has background merges, which take care of taking your insert blocks, which may be relatively small, say 1 million rows each, and turning them into much larger parts, which are then easier and faster to query quickly. And so this tiered storage allows this to happen in a very natural way, that the data arrives, drops onto the default disk. It can then and then, for example, the way I configured it, it sits there for 7 days, it merges, and by the time it gets to S3, or it gets moved to the S3 cache, it just gets pushed out and it doesn't change anymore. So there are a couple settings that are also interesting. This prefer not to merge setting is a bit controversial. Some people don't like this, but it's saying, hey, if you're out in an S3 volume, try to avoid merges if possible. This somewhat conflicts with ClickHouse's view of the world, which is it merges when it needs to merge. It's kind of like turning off garbage collection in Java. So that one's somewhat controversial, but a very good one that you definitely want to use is this perform TTL move on insert. It says that fresh data, when it arrives, do not, even if its TTL is expired, don't move it to S3. This is important because what it does is it allows it to sit there and merge a little bit before it moves to S3. So that will reduce your API calls. And by the way, one common failure is if you don't have this set correctly, you'll get rate limited on Amazon. We see that problem come up a lot. So that's why this cache is really important and this tiered storage is really important to avoid those issues. Trade-offs, I won't go through all of them because we want to get to Parquet, but there are a number of benefits to MergeTree. I think that you could summarize them by saying this is actually widely used, particularly, with separate, sort of separate S3 endpoints for each server. They're now good best practices. It just extends existing MergeTree in a kind of transparent and easy to understand way. Some of the disadvantages, an obvious one is, yes, you've got a lot of data, but people outside ClickHouse can't access it. That may or may not be an issue. You do need to manage the storage carefully, and you need to understand how it works. So because you're adding, sort of additional things here, if you misconfigure it, there's ways that that the storage can get mixed up. You just need to think about it. Backup is sort of is also a special issue here. The shared S3 data between services is a work in progress. There is a question about this, and we'll get to that, like what Altinity and others are doing about shared MergeTree. We'll cover that in the questions. But that's S3 backed MergeTree. I'm going to go ahead and turn it back over to Alexander, who's going to talk about the other option, which is to use Parquet in read-only data lakes. So take it away.
Thank you, Robert. So we were discussing about how we can store ClickHouse data in different ways. But in many cases, data is already stored somewhere. And recently, we see a lot of cases when the data is in Parquet format, somewhere on a S3 bucket. It comes from other sources. It could be some logs. It could be anything. And there are two ways to handle it. You can, of course, load it into ClickHouse and analyze that. But you can also access it from ClickHouse directly. And in many cases, this is, first of all, it's more convenient. You don't need any moving data around. And second, it is cheaper because you don't need a lot of storage on ClickHouse. You can use the object storage which already exists, and probably even somebody else is paying for that. So how ClickHouse, if you actually look into Parquet format, it is very similar to MergeTree in many respects. They are both columnar. They both use column encodings. They both apply compression. They do have some ways to optimize queries in Parquet. There is a metadata on row groups that contains information that can be used to filter the data efficiently. We know this is ordering and sparse index, very similar. Next slide. If we look into the storage structure, we can make this kind of similarity even more. So say if we have a bucket, we can think of the bucket as a Parquet table, bucket or a prefix, right? It could be Parquet table where multiple Parquet files are stored. On the MergeTree side, it corresponds to parts. So every part in MergeTree is roughly equivalent to Parquet. Yeah, but these similarities only on the surface, of course, they work pretty differently. But this is an interesting observation. At some point, we even thought about developing a MergeTree that can store data in Parquet format, which is quite interesting, but very hard to implement in current ClickHouse. Let's go next. What we can do right now? Of course, we can query data from S3 in a variety of ways, and ClickHouse supports querying the single file. If you have the URL which is pointing to the file, you can query it with a very simple S3 table function. You can query multiple files, and ClickHouse supports two types of glob patterns. First pattern allows you to do enumeration of expressions and not expressions, strings, right? And that allow you to filter multiple files. And the second one is asterisk pattern that allows to get all Parquet files from a prefix or even from hierarchy of prefixes if two asterisks are used. Of course, ClickHouse supports all kind of where clauses, and in addition to where clauses on columns in Parquet file, it can also use where clauses on so-called virtual columns. Here, file is a virtual column that maps to the object that represents a Parquet file, and we can directly reference it in a query using the generic S3 bucket glob. What can do ClickHouse in addition to queries? It can do schema inference. So if you don't know what data is stored in Parquet, you can always check it. Just use describe on a bucket, and ClickHouse will display you the structure. Of course, it's not just describe. You can create a table create a table from S3 file very easily, same way. Next slide. In addition to describe, you can also do kind of listing of a catalog. I already mentioned a file virtual column. There is also a path virtual column, which is a full path in S3. As you can see in this example, I'm listing 10 first files in blockchain data. And that allows you to understand what is inside the bucket. What about performance? Actually, performance of Parquet is quite controversial. It is pretty fast. So reads are fast thanks to parallelization, and on multi-core ClickHouse machines, it is quite fast. But it very much depends on how Parquet data is organized. For example, if you compare a single Parquet file, then it is actually pretty slow. This is a red bar on this graph. But if you use a partitioned Parquet file, partitioned Parquet data, or a bucket with multiple Parquet files, then ClickHouse can read objects in parallel streams very efficiently and get better performance. So sub-second performance with Parquet is not a problem at all. In this test, it was a local file, but on S3, it's pretty similar. But it's always very important to apply all kinds of filtering to reduce the data which is being processed by ClickHouse. If we have multiple terabytes or petabytes of data in Parquet, of course you don't want to read it all, read it to ClickHouse over the network to query every time. You need to filter it as early as possible and to transfer only necessary data. In Parquet is columnar, so if you select certain columns, ClickHouse will only read those columns and nothing else. But in addition to that, you need to apply glob filters if you can. So if you know your data, you may apply glob filter that includes date pattern, for example. And then ClickHouse on its side, it uses the data which is in Parquet files themselves. For example, instead of reading all the file, it can check min-max values in metadata, which is a header of Parquet row group, and check that the query condition is inside this min-max values or outside. And if it's outside, then it doesn't need to read the file at all. Just check the header, and that's it. Additionally, you can apply the filters by file and path virtual columns, which also help to reduce the overhead. Currently in development, we are working on Bloom filter support. So apparently Parquet supports Bloom filters that can be very useful when you query the data using some string condition, which is kind of randomly distributed. So we also think about implementing the metadata cache that will allow ClickHouse apply, for example, this min-max values filter even without checking the file. So checking the file is still expensive. It is API call. You need to read the header from S3, so its network is included, and so on and so forth. But if we could cache it on ClickHouse side, we don't need to check the file at all. This is similar to what ClickHouse do for MergeTrees. It uses this cache for marks and cache for primary key, so it doesn't need to read parts if the data is not there. It filters them on a early stage, and the same can be done with Parquet, but it requires some implementation. We made a prototype using existing tools. You can check this article, but better support in ClickHouse could be added. Next slide. It's also possible to write Parquet back. So if you have data in ClickHouse and want to export it, ClickHouse provides a way to do it. So for example, you may decide to offload your old data to Parquet and share it maybe with some applications. You can do it with this insert statement like this one. Just make sure that you use partitioning, because this is very important, not to write a single file, but write multiple files. The typical partitioning is by date. So you write one file per date, but there could be some other schemes as well. In addition to working on a single node, ClickHouse has support for utilizing the full cluster when you are working with the data on S3. This is performed using file cluster or URL cluster for files and HTTP servers, and S3 cluster for data in S3. So say if you have a cluster with 100 nodes in ClickHouse, you can use S3 cluster function and read Parquet data efficiently by 100 servers. So what ClickHouse does in order to do it, it lists a bucket. So in the bucket, it may find 10,000 Parquet files, and then evenly distributes it, more or less evenly distributes them through the processor nodes. So every node will be loading 100 files. Of course, it will be very fast. You have a linear performance increase if you use an S3 cluster. The downside, there are some problems here, but we can skip it. In addition to working with S3 directly, ClickHouse also supports data catalogs. Currently, there are supported 3: Delta Lake, Hoodie, and Iceberg. So if you have data somewhere that uses this catalog, you can use a table function similar to S3, and it will work. I just checked that Data Lake and Hoodie works out of the box, even if catalog data is not stored in the bucket. But Iceberg doesn't. It requires some metadata file to be present on S3 in order to work. But if you have it, it should work out of the box. So that's pretty much it for Parquet and S3. There are a lot of good things because when the data is already in S3, it can be accessed directly and pretty efficient. Parquet compression is in fact better than MergeTree. We were very surprised to find this, partially because ClickHouse is optimized for speed, and applying more aggressive compression and encoding, of course, is possible, but it will slow down processing. Partially because Parquet file organization is a bit different from MergeTree, that allows to apply different codecs and compression inside one file. ClickHouse cannot do it. Yeah, and data in Parquet can be used not by ClickHouse. So you can have the same data used by Spark and ClickHouse and use it for different use cases. On the negative side, the main problem is that you cannot update or delete data from ClickHouse. You can only insert, but cannot modify. Another problem is that once the data is in Parquet, there is no merge. It's not merged, you cannot merge. So the data is could be more fragmented if you write it frequent enough. There should be some external process probably that reads Parquet data and merges them to a bigger one if you want to. It's not required, but it's just an observation. And if you want to do something like what called tiering that Robert described in the previous section, you will do it manually. You'll have to do it manually. So there is no built-in support. That's it here. Let's keep going. We're almost done. And actually, as a result of this webinar, here is a short summary of things that you need to apply. First, you need to understand design patterns for ClickHouse storage and compute. This is this webinar and probably other webinars that we're doing. Understanding how ClickHouse works is extremely important in order to build large systems. Otherwise, you cannot do it efficiently. Second, and this is very important, benchmark on a small. benchmark on a small system, on a single node, and then scale it down. Don't try to deploy 100 shards cluster at the very beginning. It will never be very good. Start with a single node, make sure that you get maximum performance from it, then start the small sharded cluster, like 5 shards. Make sure that you understand how distributed queries work and how to make the most use of these 5 shards, and only then go to a bigger one. S3 baked MergeTree, it is a good approach, which works, especially when you have a lot of data. For smaller amounts of data, what smaller means is several terabytes per node. We recommend using block storage, but if your data is bigger, then S3 baked MergeTree is the only option. Parquet is interesting alternative, but it's interesting because when the data is already somewhere, it's not very interesting to write data from Parquet and use it then. But if the data comes from somewhere else, you can access it from ClickHouse quite efficiently. Kubernetes is a way to go to manage compute and storage in a flexible and very controllable way. So we highly recommend to look into that if you haven't already. And last but not least, ClickHouse is not static. It is evolving very rapidly. Every release, there are new features and a lot of features about storage, compute, object storage, and so on and so forth. So some things that we told you today may be greatly improved in 3-6 months, and new features will definitely appear. And design for growth. 1 petabyte today could be 10 petabytes in 1 year or 2 years. At some point, when I was working in a previous company, we were comparing the data size year by year. And at that time, our data size growth was 3 times every year. So steadily, in almost 10 years in a row, every year, our data size tripled. So you need to design for that initially. Otherwise, it will be very hard to scale the system later. And I think that's it. Some references. Yep.
Yep. And then how to talk to us. And we have a bunch of questions which we're going to cover, but I just want to say, here's how to get hold of us. This is a complex topic. As you can see, we jammed as much information as we could into this. If you want to find out more, come to our website, altinity.com. You can meet us on Slack. You can arrange an appointment. And then just a reminder, we have a cloud for Kubernetes that we actually have used to learn about all of these things that we're describing here. We do stable builds, which are alternative builds for ClickHouse with long maintenance. And as many of you know, we are the authors of the Kubernetes operator for ClickHouse, which was featured in this talk, but it's used for thousands of systems worldwide. And we're hiring. So if you heard this and you thought this was kind of cool, we're looking for ClickHouse developers. In fact, we love storage. If you're a storage geek and want to work on it, give us a call. So Alexander, let's look at some of the questions here. I
keep answering them, but we probably can discuss some of them.
We can discuss some of them. You know, there was one good one here, which is here. From our one of our friends, is there any ongoing open source implementation similar to shared MergeTree on your part? If any, can you please provide any update about it? Maybe you could just describe our plans for what we're doing in this area.
Yes, that was a question from Ramazan, if I recall correctly. Yep, shared MergeTree is a great feature of ClickHouse Cloud. And a few months ago, we started a community project to implement not a replacement of shared MergeTree, but improve ClickHouse support for object storage in a way that would allow users to use it efficiently. Because shared MergeTree by itself is not needed for many users, but some features that shared MergeTree provides, they are needed. In particular, the clear separation of storage and compute, the zero copy replication that currently exists in ClickHouse is kind of for this purpose, but it is not very reliable. It is buggy. So what we started in September is to do a replacement for zero copy replication, but that hasn't been complete yet. Another track that we're working on is to improve S3 plain storage type, object storage type. It is different from the existing S3 implementation. It already exists in ClickHouse, but it has limited functionality. However, the way it stores data in S3 is much easier to understand and much easier to maintain in the long term compared to what existing MergeTree over S3 is doing. And in particular, if S3 plain is used, then it's very easy to do the separation of storage and compute because the data which is in S3 plain can be plugged without any additional manipulations to any ClickHouse compute because it already contains all information about the data and metadata, and you don't need this shared MergeTree because the shared word here is for sharing the metadata properly across multiple ClickHouse nodes. But if metadata is baked inside the data, then you don't need sharing. So it's in progress, and we hope to deliver something by end of this year.
Alexander, there's a related question on this, which is I wish ClickHouse can auto-detect each other in a cluster and allow shared S3 path to represent a table. Right now, the notion of host is strongly built into ClickHouse data. Can it evolve in a way similar to Spark, where the compute connects to S3 and without a query plan then executes?
Yeah, this is of course a way to go, and I think this is partially available in ClickHouse Cloud. They have this dynamic cluster configuration, and we can expect that an open source version will support it in the future. We hope so.
And it's worth noting that the S3 cluster command effectively does this. When you're reading Parquet, it will just grab as many resources as it can and go read the files independently across a bunch of hosts. So that's kind of cool. There's no setup required or coordination.
Yeah, just to get a little bit more light on that. So ClickHouse already can do it. There's a feature which is called dynamic sharding. So say if you have 10 replicas, it is kind of strange use case, but say you have one data and 10 replicas, then ClickHouse can execute the query in a sharded way. It's quite unusual, but in a sharded way. So instead of when you run a query, instead of executing on a single replica, it can split the data which should be queried across these 10 replicas because every replica has a copy of the data, and then load it efficiently as a distributed table. Next step, you have 10 replicas looking at the same S3 data at S3. Here we have one copy of the data and 10 processing nodes. So it's already available, but not a bit limited. So you can have 10 replicas, but if you have 100 replicas, it's probably not going to work.
Great. So next question. I have a table defined with TTL delete. I assume I can use alter table modify to change this to TTL move while continuing to use this table. Presumably, I'd want to freeze, modify, and unfreeze the table. What would you recommend in this case?
You don't need to freeze, modify, and freeze. You can do it alter table modify on the working table.
Yep. Great. So that's a pretty flexible operation. There was somebody who asked about an internship I've just sent you. I hope you're still online. I've sent you an email to send your resume to. Just go ahead and send it there. Here's one. Does the use of file formats like Delta Table or Iceberg provide any benefits for ClickHouse in terms of performance? And I think you were typing an answer, but you could just answer that.
Yes. Delta Lake and Iceberg, it's not a file format, it's more catalog. You can store Parquet in those catalogs. So there is no performance benefits. It's just a matter of organizing the data.
Great. Here is a wonderful question from Arnaud. Thank you, Arnaud, for this. What do you recommend to back up S3 back MergeTree? ClickHouse backup or the backup command?
In fact, for S3 back to MergeTree, ClickHouse backup can use a backup command internally. We of course recommend ClickHouse backup because it allows you to build infrastructure. It's infrastructure. It's a tool. It's not a command. With backup command, you don't. You later don't know where your backups are located. ClickHouse backup, we have the end-to-end solution. And internally, it can use backup comment. It has actually two ways to backup S3 in our table. It can use a server-side copy, or it can use embedded backup.
Okay, so we recommend ClickHouse backup, but of course we manage it, or we maintain it too, so we're just maybe a little biased, but it's been very, very widely used. Great. Oh, question here. Can you share the presentation? Yes. If you signed up for this, which you must have to get in here, you will get a copy of the presentation as well as this video within 12 to 24 hours. Let's see. So when you say keeper is not required for data rep, I think this says not required for data replication. What do you mean? Do you mean to say that keeper only maintains metadata and the data is transferred directly from the primary shard? I think this was.
Now, I think there is some confusion. I sent the
Yeah.
link to replication using distributed table. So this is pretty interesting technology to sync data between different clusters. And only for this one, keeper is not required.
Right. Yeah, in general, you always have to use keeper for replication because it for data replication inside MergeTree, because that's the thing that remembers which parts are available on which servers. There's an unrelated or an off-topic question here, but a good one. Can ClickHouse be used as a vectorized database for RAG with LLMs?
I have no idea. We haven't seen this use case.
We don't exactly. So we haven't seen this use case. You can use ClickHouse as in theory, use it as vectorized DB or a vector store. There are things like nearest neighbor search. We haven't benchmarked them, and currently we don't have too many users. Users are looking at AI, but this actually is not one that is very prominent at the moment. But check around. There's, I think ClickHouse Incorporated had at least one article about this that you might check out. So we're 10 minutes over time. Let me look back and see if there are any other major questions that we want to just cover. Yeah, let's see. Alexander, were there any other questions that you answered that you wanted to highlight?
No, if there are no follow-up questions, I guess the guys who had follow-up questions, they were not shy asking them.
Yeah. Thank you so much. I'm looking at one that I do want to. There's a question here that you answered. Can I change the storage policy for existing tables? The answer, as you said, is yes, but please, please, please do it very, very carefully. If you're a support customer of Altinity, give us a call before you do it. The thing you want to avoid is doing anything which would alter the endpoints that you're writing to. That will create a huge mess if you somehow change the location that ClickHouse is using to store this backing data for MergeTree. If you get that going to two locations, it's going to be a painful cleanup. So give us a call. Other than that, just be real careful out there. We will, by the way, we have blog articles in progress right now that will be coming out. Watch our blog. A lot of what you're seeing here, for example, on S3 and Parquet, is already out in blog articles, but we're putting more stuff out as we learn more, get more experience, and find additional places that where guidance is helpful. With that, Alexander, thank you so much for doing this presentation together, and thank you all for attending. If you have further questions, look us up. Come to altinity.com, join our Slack. We're happy to answer questions. This is a major area of focus for Altinity, and we're here to help. So thank you very much, and have a great day, everybody.
Thank you, Robert.